Okay. Can you see my screen?
Yes.
Okay, super. Okay, yeah, so for those that haven't met me, so I'm Justin Alsing. I'm actually a bit of an imposter here because I'm really a cosmologist, but I've worked a lot on applying likelihood-free methods in cosmology. So I'm actually going to ambitiously split my talk in two. So I'm first just going to give an overview of density estimation based likelihood-free methods. So in my community, we've been kind of developing likelihood-free machinery in parallel to and largely ignorant of the kind of ABC community. So I'm going to give a broad but shallow overview of the way that we think about it, in the hope that there might be some talking points and interesting nuggets in there. And then the more fun thing I'm going to talk about is applying similar kind of ideas to Bayesian decision-making under intractable likelihoods. Okay, so those of us that think about density estimation LFI, we say, okay, we can do simulations and draw, data and parameters from their joint distribution. So the question is, how do we do density estimation on this simulated cloud of points to extract the posterior in the most sensible way? So broadly speaking, there are three ways that one might go about this. So the most obvious thing you might do is just draw parameters and simulated data and just fit the joint density, okay? And then if you take a slice through that, your observed data summaries, then you get your posterior out. So this is nice in the sense that compared to traditional ABC methods, there's no epsilon and there's no distance metric, and use all the simulations. So it tends to be quite simulation efficient, and you can get high fidelity results. You don't have to have some epsilon threshold that puffs up your uncertainties. However, it does have some drawbacks. So, it typically involves doing density estimation in relatively high D over both your parameters and summaries. And doing it this way where you fit the joint, you also, you either need to draw parameters from your prior, or you need to importance reweight if you want to adaptively adapt your proposal density, which makes for extra noise in the density estimation step. So how can we improve this? So the next most obvious thing to do is to do conditional density estimation and learn the posterior as a function of the summaries. So this is nice because we've actually made the density estimation task easier here. So we're doing density estimation over fewer parameters. It's only over the thetas now. And the data dimensions have kind of been put, instead of as density parameters, they're kind of regression parameters now. And the general rule is that, the more things you have on the right-hand side of the vertical line, the easier your density estimation task is. So regression is easier than density estimation. So this typically requires far fewer simulations to get high fidelity results. But if we want to do adaptive proposal, have an adaptive proposal density, then we still need to do importance reweighting, which adds noise to the density estimation. So the third thing one might want to do is flip it around and say, okay, well, let's just learn the sampling distribution of the data summaries as a function of the parameters. So this gets rid of this last limitation. So now, because the theta is no longer a measure that we're trying to learn, you can simulate at whatever parameters you like. So you can do as much active learning as you like. So in our community, at least, we've kind of settled on this as the standard way of approaching likelihood-free inference tasks. So just to summarize, what we do is we simulate data and parameters. We do conditional density estimation. And we do this iteratively. So then we update our proposal, do more simulations to get more close to the bit that we're interested in, where the data actually sat, and iterate around and around. Okay, so in order to do this, there are a couple of bits of machinery that one needs. So one needs to be able to do conditional density estimation. So we'll just talk about how we tackle that briefly. And of course, there's the perennial or constant question of summary statistic choice. So I'll discuss how we think about that in our community as well. Okay, so conditional density estimation. So I know some people have talked about ways of doing this already today, but broadly speaking, our methods for conditional density estimation fall into two groups. So we either use mixture density networks. Okay, so these are quite simple models really, where we model the sampling distribution of the summaries conditioned on the data as a mixture model, for example, a mixture of Gaussians, but it could be any mixture model you like, where the weights and the means and the covariances, or whatever mixture component parameters you have, are functions of the parameters that you need to parameterize somehow. So we want to use a generic function approximator to parameterize those things. So we typically just use a neural network. So this is a neural network that takes parameters in, and it spits out the mixture model parameters for those input parameters out. Okay. The second class of conditional density estimations that we typically use are normalizing flows. So in this case, we just have a function that takes us from some base distribution, like a unit normal, to the target, where the bijector that takes us from the base distribution to our target, we need to parameterize. So there's a huge literature now on parameterizing this using neural networks in a smart way. Okay, so this is typically what we do. We use a combination of these to do our density estimation, and it works really nicely. And in order to fit them to the simulated data, we just minimize a estimate of the KL divergence between the target and the surrogate sampling distribution model. Okay, so effectively we do maximum likelihood fitting of the density estimator models to the points. Okay, so summary statistic choice. So I'll just give an overview of how we think about it. A lot of these ideas are very standard, but there might be some new stuff in there. So we typically have three approaches to defining our summary statistics. So for lots of problems in cosmology, we actually have an approximate likelihood. So this is related to a comment that someone made this morning, where if you have an approximate likelihood model, under those assumptions, you know what the optimal summaries are. They're basically the maximum likelihood estimator under that likelihood, or equivalently, it's the score of that likelihood that is the quantity that saturates the Fisher information content of your summaries. Okay, so obviously, in the context of ABC, this is only useful in situations where you have an approximate likelihood model, which is not necessarily that common. But as a concept, it does provide a guiding hand for other approaches to doing automated summary statistic choice, as we'll see. So the other popular thing to do that I know people use a lot in your community too is just using a neural network to get your summaries. So again, this was discussed this morning, but if you train a network to basically just take data in and estimate your parameters, minimizing the square loss, then you get something that estimates the posterior mean, which is optimal in a broad class of situations, but not always. But it's a very powerful tool for us, at least. There is a third way that I think is pretty cool, and I haven't seen in the ABC literature that kind of uses both of these ideas. So one of the disadvantages of training a neural network to find your optimal summaries is it needs to be done globally usually. So, you need to give it simulated data over a broad range of parameter values, and it needs to learn an estimator over that whole range. And that can be quite simulation expensive. So how about if we took the same idea of using a neural network to find out optimal summaries, but rather than estimating the posterior mean, we explicitly get the network to saturate the Fisher information content of the summaries about some fiducial point. Okay, so let's just think about how this works for a second. So what we do, we take our network, we feed it simulations around some fiducial parameter values that we think is a good starting guess. And we also feed it simulations that are stepped plus or minus epsilon from our fiducial point. Okay. Now, because we have simulations at the fiducial point and stepped forwards and backwards, that allows us to estimate the Fisher information content of the summaries that come out, okay, under the assumption that they're Gaussian. Okay, so the Fisher information is just the gradient of the mean of your data with respect to the parameters, hit with the inverse covariance times the gradient of the mean again, okay, and take the trace. So the stepped simulations allow you to estimate the gradients, and having a bunch of simulations that you fed in at the fiducial point allows you to estimate the covariance, okay? So our loss, in this case, rather than having a mean square error, our loss is just the determinant of the Fisher information, the estimated Fisher information. And this turns out to be really powerful. It gets around a lot of the issues that just standard regression of the posterior mean has. It's much more simulation efficient because you only need to do it locally around a particular parameter set. And if you're worried about it only being locally optimal, you can bolt together summaries estimated at a few different fiducial parameter values to get more information out. So this is cool. The other thing that we do a lot in our community is nuisance hardening our summary statistics. So we're very often in a situation where our model has lots of parameters, but most of them are nuisance parameters. And usually there's only a couple of things we actually care about. So it's interesting for us to ask the question, what are the optimal summary statistics that are as informative as possible about the parameters we care about, whilst being as insensitive as possible to the nuisance parameters that we ultimately want to marginalize out. So we can answer this question in the context of these three compression methods. So for the score compression, you can just do the same thing, take the score of your surrogate log likelihood model, but having marginalized out your nuisance parameters beforehand. And it turns out that this is equivalent to just taking your original summary statistics using the score and using the Fisher matrix to just project out the correlations basically between the parameters and the nuisance parameters. For neural networks, it's much simpler. You just keep the nuisance parameters in your simulations and just treat them as noise, just ignore them. So you just estimate the marginal posterior means. And for these information maximizing networks, you can use the same trick that we use for the score. You can use the inferred Fisher information that you estimate from your network to project out the nuisance dependencies. Okay, so for us, this idea has been really powerful in allowing us to keep the dimensionality of both our parameter and our summary statistic space small, even when there are lots of nuisances that need to be marginalized over. Okay, so that's kind of like a cosmologist's view on how we do likelihood free inference in our community. So just to summarize, to get summaries, we either use the score if we have an approximate likelihood, or we use regression networks or these IMNNs, possibly nuisance hardening. And to do the likelihood free inference step, we do conditional density estimation with adaptive proposal densities. And we have two public codes that are widely used in our community that I encourage you to try if you fancy it. One of them for doing the density estimation based LFI, and one for doing the information maximizing neural networks. So it would be cool in terms of the context of summary statistic choice to look at the comparison of the IMNN to other things that are being developed and being talked about this week, because I think it's a cool idea and it would be nice to have some comparisons there. So in cosmology, the kind of performance we get with this overall framework is the kind of word or the kind of sentence that people bandy about is that for 6 or so parameters, we can get away with 1,000 or so simulations and get pretty high fidelity posteriors out. So this plot on the bottom right is just a benchmark case, our kind of classic benchmarking problem in cosmology, estimating 6 parameters from a classic supernova cosmology data set, where we actually have a known likelihood in this case, and we see that we get really quite high fidelity posteriors out with about 1,000 sims. Okay, so now for the more fun part. So the question is, can we use the same kind of ideas when what we really want to do is make Bayesian decisions in situations where we also have intractable likelihoods? Oops. So for real world problems, what we often really want to do is take the action that maximizes some expected utility under our uncertain knowledge about the state of the world given our observations. Okay. So let's just set up some notation quickly. So action I'm going to call A, observations or summaries thereof I'm going to call X. Outcomes is, what happens in the future that affects, how much money you make or how many people die or whatever. I'm going to call Y. Model parameters, state of the world, theta. We have a utility, which is typically profit or, negative cost of some sort, and expectation thereof. So mathematically, the problem is we want to find the action that maximizes the expected utility under the posterior predictive distribution for the outcomes given our data and model. Okay, so let's just set up a really simple example that we're going to work through to the end, and I'll show you some results on using our new methods. So just to illustrate how this works for people that don't think about decision problems every day. So let's imagine you're in charge of a warehouse and you want to know how much stock of a particular product should I fill my warehouse with to maximize my expected profits. Okay, given that I don't know what future demand is going to be, but I have some historical data about what demand has done over time. Okay, so in this case, your action is how much stock do you put in the warehouse. Your outcome, the thing that you don't know, is how much demand is there going to be for your product next month. Your utility is basically how much money you make. So it's, how much do you make from your sales minus how much did it cost you to store things in the warehouse. And we're also going to apply a penalty for being out of stock because, if you're out of stock halfway through the month, you might lose a lot of customers. Our observations is, time series of, demand for your product over time. And our state of the world is the unknown parameters of that time series model. Okay. So naively, if you wanted to solve this problem, finding the optimal action, first thing you need to do is the inference, okay, which if we have an intractable likelihood is already challenging. Then we have to figure out how to do these integrals, which is also difficult because even if your posteriors are tractable, the posterior predictive distributions are often intractable or challenging. And then we need to figure out how to optimize that thing with respect to A. Okay, so, from a naive perspective, this is a pretty hard problem as it is, and it's even harder under intractable likelihoods. But it turns out we can cast this as a conditional density estimation task, much like the way we do likelihood-free inference. Okay, so the thing that we care about here is the expected utility, which we can really think about as just an integral of the utility over this distribution of realizations of the utility conditioned on our observations and our action. Okay, so this P of U given our observations and action is a distribution that exists and we can simulate from it, but we don't know what it is and we care about its expectation. So what we're going to do is say, okay, let's learn this thing. Okay, let's do forward simulations and let's do conditional density estimation to learn this thing. And let's do that in such a way where we explicitly learn its expectation value as a function of action and data. Okay, so for example, we might parameterize that as a Gaussian, where the expectation value and the variance are functions of observations in action that maybe we parameterize with a neural network or otherwise. Okay, where the only thing we actually care about is the expectation value. Okay, so we can be a bit fast and loose with getting the assumptions about the shape of the utility distribution right. We also only care about the expectation value in the neighborhood of the optimal action and the data that we actually observed. And in case it's not obvious, once we've trained a neural network to emulate this thing, getting the optimal action, optimizing it is easier, can be done in a jiffy. Okay. So we're going to simulate, so draw parameters, simulate observations, choose some action to look at, simulate the future and compute the utility. We do that lots of times to get our training set. We take our simulated data, utilities and actions to do conditional density estimation in a way where we learn the expectation value. Okay, so we've turned this, what was quite a nasty problem, now into a one-dimensional conditional density estimation task, conditioned on n summaries plus n actions numbers. Okay, so in situations where your action is a low-dimensional quantity and you don't have that many summaries, you know, at face value, this is easier than the inference task that you would have had to solve on the way anyway. Okay, and it bypasses doing the inference first. So you just go straight to getting the optimal action. And if we want to go even further, we can put an ABC style distance metric in there instead. So we can learn P of utility given the distance from the data that we observed and action. Okay, so now we've squashed the dimensionality down even more. And then we can just calculate that thing at 0 distance in the end. Okay. And of course, we want to do this in an adaptive way. So we sprinkle a bit of active learning in there. So we do simulations, we get training data. We do identity estimation to infer the utility distribution, but we can also do inference at the same time, okay, to optimize the proposal density for the parameters, okay? So, so we can do this in an adaptive setting where we iteratively update both the distribution of the actions that we choose to look at based on which ones look like they're close to the optimum, and the parameters we choose to simulate at based on which ones give us data realizations that are close to the actual data in ABC style. Okay, all right, so let's do a quick example of this warehousing problem. Okay, so remember, we want to know how much stock to put in the warehouse to maximize our profit. Our observations are our time series of demand. So let's say we've observed over the past 12 months how much demand there was. And we're going to compress it down to just a mean and a variance of the demand time series. And, you know, let's keep it super simple. Let's say our model is just that demand is, you know, IID Gaussian with unknown mean and variance. Okay, so very simple problem. Still quite challenging to do though, if you have to do all those integrals and do the optimization in a naive sense. So we're going to do simulations that learn the utility distribution and optimize it at the same time. And this does really, it does really nicely. So after just 128 sims, it's already getting out a decent estimate of the optimal action, which I got by brute force, and a nice estimate of the expected utility. And obviously, if you bump up the number of sims, you know, your inference of the optimal action squeezes down. It doesn't squeeze down much more than that actually as you do more sims, because the utility is pretty flat in that neighborhood anyway. So I appreciate this is a very simple toy problem, but I think it's pretty cool nonetheless that you can effectively do, you know, do those integrals and optimization with just 128, you know, Monte Carlo realizations. Basically, I think this is cute. So it works. So let's do a bit more of an involved example. Okay, if I have time. I can't see the clock, so we have time. Okay, so let's do a really fun example. So let's imagine that you're the mayor of an island, Svalbard, maybe. And on the island, there are deer and there are wolves whose population goes up and down with time. And you've been monitoring the population because when the deer population surpasses some threshold, the deer start eating the crops and it costs lots of money. Okay. So we get to the current time and we've been observing what's happening and we say, oh crap, the deer population is going up quite fast and the wolf population is going down. So there's a good chance that there's going to be a big spike in the deer population. And because we're God in this world, we can say, well, yeah, there is a pretty good chance. This is simulating forwards from the true parameters that the deer population is going to be high. So we're going to plan a cull. Okay, so the question is, how many hunters are we going to employ and for how long? Okay. And the utility that we want to optimize in this case is, well, we want to minimize the cost induced by the deer eating the crops. And there's also the cost of paying the hunters as well. Okay. And we're going to use this much loved Lotka-Volterra model. I think most people are familiar with this because it's an ABC classic testbed, right? But basically it's a predator-prey model where, you know, the deers and the wolves are born at certain rates. The wolves can die at a certain rate, and the wolves eat deer at a certain rate. And for certain parameter values, you get oscillatory population dynamics. The outcome, so the future that we don't know, is what the deer population does as a function of time. And our observations are just 9 standard summary statistics of these time series. So it's like the means, log variances, and lagged correlations of the time series. Okay, so we're going to play the same game. We're going to learn the utility distribution conditioned on our summary statistics over the action space and see if we can tease the optimal action out. So we can, right? So this is a pretty hard problem to do, right? So I had to do it by brute force to know what the truth is, which is the little black X. And it took like millions and millions of sims. But doing it this way, casting it as a conditional density estimation task, it converged after like 80,000 or so sims. And we get a pretty nice estimate of the optimal action in this case. So some caveats here. Actually, to do this, I only did active learning over the action space, not over the parameters. So I'm not doing any inference here at all. So all the simulations are from the prior, which was, you know, weakly informative in this case, so that we didn't just have too much prior volume to simulate from. So I think we'll be able to do a lot better by using active learning in the parameters as well. And I'm just using very rudimentary conditional density estimator in this case, and it still manages to get the right answer out quite quickly. So, so you know, I don't know if this is interesting or not. I think it's cute. I don't know if it's been done, and we just haven't been able to Google the right words. But I'm curious to get feedback on, you know, whether people think this is fun or cute or useful or not. So just to summarize, you know, we can cast these decision problems as conditional density estimation tasks and bypass the inference step completely. And those tasks are often, but not always, easier than the inference task that we would have had to solve along the way. Our initial tests look pretty cool, and there's lots of work to be done here on optimizing it and comparing it to other approaches, etc. Okay.
Thank you. Are you done?
Yeah. Yep.
Okay. Thanks a lot, Justin. So are there any questions? Well, I'll start. So I had a couple of questions actually. One is, so you put this density estimation on the utility, but it's not at all clear that in the examples that you showed that the utility was absolutely continuous with respect to Lebesgue measure. So what happens then?
Sorry, if it's not continuous.
So, like for instance, like I mean, I might have totally misunderstood, but from what I understood in your the first example, the toy example, so the utility was defined like you had this mean of y and blah blah blah, and then so you had this sort of some sums of means and max of things.
Yeah.
And it's, so you have obviously the utility function is not absolutely continuous with respect to Lebesgue measure. So if you fit the Gaussian density on you, what does that, well, I mean, don't you run into trouble?
Yeah, exactly. So, so you might, but we haven't run into trouble yet. So this is an open question. I don't know what happens in those situations, but you know, we haven't run into trouble yet. I think in this case, think it's not as bad as it looks, right? Because for any given action, then I think the utility is continuous. Okay, you just end up with integrals over your posterior predictive distribution that are truncated. But I'm sure for
it's not that it's continuous. It's more that it has no density with respect to Lebesgue measure, because with positive probability, it's equal to these fixed values. No, isn't it?
I'm not sure. So if you, for this utility here, if you take a given value of your action, right, then your utility is a linear function of y in that case, where some of those terms will either be turned on or off, depending on the value of y compared to a. So yeah,
I see. Yeah. Okay. So in your example, so it has a density.
In this example, I think it does. I'm sure there are examples where it doesn't, and you might run into problems. It'd be cool to see what happens in those cases. I think
there's a point mass for.
Yeah, so there is a point mass, but in the same time, it's also a y. So it's either when you have a point mass on the left-hand side, you have not a point mass on the right-hand side. So maybe it makes a compensation, which it's not clear, but it's probably true. Then I had something I was again lost. At some stage in the first part of your talk, you said that you wanted to localize around theta.
Mm-hmm.
Star, but don't you want rather to localize around the data point? I was a bit lost there.
Right. So you mean for the information maximizing network?
Yes. Yeah.
Right. Exactly. So, so this is motivated by two things, I guess. So for us as cosmologists, we've been measuring the same 6 numbers for the last 200 years. So we already have a pretty good idea of where those numbers are. So we really only care about having optimal summaries in the neighborhood in some neighborhood of parameter space. It's also motivated by, in cases where the likelihood, you can form locally optimal summaries by taking the score. And those typically do pretty well, even when you're not that local to the fiducial parameter points. And it means you can be much more simulation efficient in terms of computing the summaries if you just do it locally.
Thank you. So there is a question by Denis. Yes, Denis his microphone is not working. So I might have missed this in the talk, he says, but how do you suggest choosing the fiducial parameters?
How do we use them?
How do you suggest choosing the fiducial?
How do you choose them? Okay, good. Yeah. So as I say, for us in our community, we always have a good guess for the parameters.
Yeah. Okay. So that was the same question. Okay.
So that's a bit of a special situation, but there are well-motivated schemes for iterating this. So with these information maximizing networks, they effectively give you an estimate of, they give you a crude estimate of the maximum likelihood parameter values and the gradient. So you can use it to iterate towards the peak. Or, you can choose a fiducial point, do a bit of ABC or LFI otherwise, and then choose a better fiducial parameter point and then retrain your network. But yeah, it is a bit fiddly. Yeah.
Any other questions? Okay, so let's thank Justin and all 3 speakers actually for this last morning session. And I guess like we're going to see each other after some break, no?
Yeah, so this is resuming in 2 hours and a half. So in French time, it would be 3:30. In UK time, it would be 2:30.
Thank you.
So thank you, everyone. Have a good break or chat online. We can keep the channel open.
Bon appétit.
Yes.
I'm going to have some.
Le resto est fermé, Julien. Hein, tu vas avoir du mal.
Oui.
See you later.
See you. So I leave the channel on. Anyway.
Thank you.
Okay.